Hey, welcome to my class. If you're looking at this through my YouTube videos, you'll notice that this is actually a little bit backwards. So this is the introduction to my Calculus 1 class, my differential equations class, and my previous videos was actually the conclusion. And this is because of the COVID-19 quarantine, when we are all forced to move all of our teaching materials online. So, since I had the last third of the class being Laplace transforms, I figured I would go ahead and volunteer to do this over the summer. So, welcome to my summer class. So this is differential equations from the beginning. So, a differential equation, what that really is it's an equation that involves derivatives. So, just like we have at algebraic equations being like, say, y is equal to the square root of 1 minus x squared, which gives us a circle. Differential equations actually involve derivatives. So it could be something like the derivative of y with respect to x is equal to y, or in other words, the derivative is equal to itself, or in other words, it basically is the exponential function. And so the idea is that we want to be able to start with a differential equation and solve it, just like we would or a regular algebraic equation. And so this is going to involve some tools from calculus, as you'd expect, and we're going to find various ways of twisting ideas like the chain rule, and that's going to come up with separation of variables. We're going to use product rules, and that's going to be used to solve what we call linear differential equations. And then, of course, we're going to have a whole ton of other integration techniques that are going to come into play. So integration by parts is going to come into play all over the place in solving these differential equations. Most of the time, we're going to be trying to set up the differential equation so we can actually just integrate it and get an answer. And so, if you're not comfortable with integration, it's a really good time to go back and review some Calc 2 concepts. We'll review them as we go, but can't do absolutely everything. So, what we're going to do to begin with, though, is we're going to introduce a lot of basic concepts, such as the existence of differential equations, and this is called the Picard theorem. And we're also going to talk about some qualitative methods and quantitative methods of examining differential equations. The qualitative methods are basically, we're going to make a whole slope field, a whole bunch of little tick marks representing slopes at various points in a plane. And then the idea is that we would like to follow that to sort of get an idea of what a differential equation will look like. It's sort of like when you graph a polynomial, you find its roots, and then when it's positive and negative, and that sort of gives you a rough idea of what a polynomial should look like. So in this case, the slope field method and the finding of isoclines, which we'll define later, are going to help us understand what the solution to a differential equation must look like. It's of course not going to be exact, just like with the polynomial. We just know it's above here and wiggles around like that. So then if we want to get to be more precise, that's what we turn to quantitative methods for. For instance, we have Euler's method, which is basically it chooses a fixed step size, and then one by one we will sort of guess where the next solution should be based on an algorithm. And this is Euler's method, and it's sort of a first-order method of a whole collection of methods, and one that's also commonly used is called Runge-Kutta. And so we might talk about that a little bit, but Euler's method is something you can actually do by hand. So in any case, that's going to be basically chapter 1 that we're going to talk about, and then after that we're going to go to chapter 2, which is where we're going to do the studying of actually using calculus to solve some differential equations. So we're going to do things like separation of variables. We're going to do things like solving linear differential equations, and then some exact equations too. And after that, we go briefly into chapter 3. Section 3.2 is really what I like to include, which is sort of like the word problem section of this class. And so there we're going to talk about things like basically like water going in and out of containers and relating these rates, so that's a really good section to cover. But then after that, we're going to jump into chapter 4, where we're going to learn a whole bunch of techniques for solving linear differential equations with constant coefficients, and this is going to include what's called a characteristic equation. And so we'll do about like 5 or 6 of the sections out of chapter 4, and then we'll jump ahead up to chapter 7 and do Laplace transforms. If you want a preview of what Laplace transforms is all about, you can go check out my other videos that are already posted. But yeah, so that's going to be the class, and so we're going to go ahead and jump into it and talk about a lot of these basic definitions and terminology to help you understand what we're going to be doing later. In any case, yeah, that's it, and yeah, let's jump into it.
Okay, so let's get started. If you're following along in the book, this is the book by Nagle Saff and Snider, Fundamentals of Differential Equations. And this is in the 9th edition. So if you are following along, then this is going to be from basically section 1.2. 1.1 is a bit of background, and if you have the book, you can go ahead and read it. But the real content of this chapter starts with 1.2, and actually that seems to be the case with most of the chapters in the book. The second section is where you really get into the meat of things. So what are we going to be talking about today? So first, we're going to be talking about what it means to be a differential equation. And then we're also going to talk about solutions to differential equations. And so this is going to include, say, implicit solutions, which we're only going to be talking about on occasion, and then explicit solutions. Okay, so those are going to be the solution types we're going to look at. Explicit solutions are generally things that you can look at and you can evaluate immediately without having to do any extra solving. Whereas implicit solutions, the output, you have a sort of your dependent variable y. It's going to be mixed in with a whole bunch of other things, and so you'll have to use things like implicit differentiation in order to see if it satisfies the differential equation, things like that. Other things we're going to talk about are initial value problems. And these are sort of, so a lot of the differential equations we're going to be looking at, we're going to find a solution, and one thing that we're going to do is we're going to find a solution that's going to have a whole lot of free variables. And that's partly because when you take a derivative, you kill off constants, and so when you integrate back up, then your constants can end up, showing up again. And so, if you want to have the most general solution to a differential equation, then you need to keep those constants in there because they're sort of free. Now, if we want to keep them from being, like, say, free variables, or say not free variables, but arbitrary constants, and want to pin those constants down, you need extra conditions, and that's going to come down to your initial values. So, for instance, we could be talking about the position of a particle. So, we know that, say the second derivative of x with respect to t, it might be equal to minus the gravitational constant, right? And we remember back from Calc 1, then if we want the first derivative, it could be like, say, minus gx plus some constant. And in this case, this would be our initial velocity. And if we want to integrate up again, then we'd be at minus gx squared over 2 plus v naught times x plus, t, not x, sorry. We're integrating with respect to t. So it should have a t here, it should have a t here. Sorry, I just had lunch. and then we're going to have our initial position. And so the initial conditions that we're going to have, and in this case we know them already, of being initial velocity and initial position, are going to help pin down exactly what the final equation is going to be. So in this case, we we haven't actually said what these things are. We just gave them names. And so this is still a general solution to this particular differential equation. Okay. And by the way, this is a particular case of a differential equation straight out of Calc 1. This is a very simple one because this side doesn't involve anything involving the dependent or independent variables. So we can just integrate that and solve this problem immediately using tools that we already have. But let's go ahead and continue. And so what we're looking for ultimately is the whole point of the class is to come up with solutions given a differential equation. And so what we're going to, but we need to be able to guarantee that there is going to be a solution. And so that brings us to this last bit where it's going to talk about the existence and uniqueness of solutions. Okay, so that's what we're going to talk about. All right, so let's go ahead and get started. So the big question is, what is a differential equation? I apologize for my handwriting. So what is a differential equation? Well, in general, a differential equation is an equation that involves a derivative. So, for instance, and this is pulling a little bit from section 1.1. So basically, let's just say a differential equation is an equation that involves derivatives. So in particular, we have things that are called independent variables. And in this case, what do they mean? Say variables. Spell it right, yeah, okay. Independent variables, so these are variables that don't depend on any other ones. That don't depend on others. Okay, and a dependent variable is a variable that depends on other variables. Okay. So, if we take a look, say an algebraic equation, say 1 minus x squared, so equation for the top half of a circle, then in this case we would have x would be an independent variable, and this would be a dependent variable. Okay, but we're talking about differential equations. This is not a differential equation. Not a differential equation. A differential equation is usually an equation that involves a derivative. So say dy dt is equal to say t times y, and in this case t is an independent variable and y is a dependent variable. Okay, so I should say this is really coming from section 1.1 out of the book. But yeah, so this is a differential equation. This is a sort of first order differential equation, and we can actually solve it pretty quick. So for instance, this is using the method of separation of variables, which we'll go into more detail. I don't expect you to be able to do it yet. But basically what this can turn into is you multiply both sides by dt, and you divide by y, and so then you get dy divided by y is equal to t times dt. And we can go ahead and integrate. So this gives us natural log of the absolute value y is equal to t squared over 2 plus a constant. And then if I exponentiate both sides, then I get, say, e to the absolute value of y is equal to, e to the natural log of the absolute value of y, which, by the way, is equal to the absolute value of y, is equal to t squared over 2 plus c. And now I'm just going to make an assumption on the side here, just for assumption is that y is going to be bigger than 0. And so then this gives us that y is equal to e to t squared over 2 plus c, right? And so there you go. And here we have one of these arbitrary constants coming up again. Okay, so a differential equation is an equation that involves derivatives. So here we have one derivative. This is what we call a first order differential equation. Okay, and in fact, this is what we call an ordinary differential equation. Right, and now what makes an ordinary differential equation versus what is called a partial differential equation? So an ordinary differential equation has only one dependent variable. Or independent variable, sorry. Whereas a partial differential equation has multiple independent variables. Okay, so an ordinary differential equation, we saw one already. So dy, say dt is equal to ty is an example of one. We could also have what we call a second order differential equation, dy dt squared plus, say, dy dt minus 5y is equal to 3. And so we still only have one independent variable. But a partial differential equation would be something like this: partial derivatives, because now it's multiple variables. So now we have partial derivative of u divided by partial derivative t minus partial derivative of u, say partial derivative of y. Let's say y is an independent variable in this case. Is equal to e to the y. So here, this is independent variables. And we have a dependent variable here, u. In the other case, we had a dependent variable here of y. So this is a partial differential equation. And we denote this as a PDE. And this is an ordinary differential equation. And this we call an ODE. Our whole class is about ODEs. We might talk briefly about PDEs at the very, very end of the class, but generally speaking, this whole class is dedicated towards the solution of ordinary differential equations. Okay. So, now that we're clear on what those are, let's see. Any other definitions we need before we can jump into the rest of section 2? Linear differential equations. So that's important. So a linear differential equation is an equation that is sort of linear in the dependent variable. And so, for instance, say dy dt times y plus 2 is equal to 0. This is what we call nonlinear. And the reason why is because we have a y multiplied by another y. Even though this is the derivative of y, that sort of counts. And so, for instance, y squared plus dy dt is equal to, say, 0. While this term is a linear term, this term is a quadratic, so this is, again, nonlinear. But we can have other things. So we can have the second derivative of y with respect to t plus y is equal to, say, 25. This is linear. This is just an operation applied twice, but that is not a squaring operation. So that's a linear term. And so in general, the book tells you that you have a linear differential equation if it could be written like this. So let's say we have an independent variable x, then we have a sub n of x, dn by dt x to the n, so the nth derivative of y, plus a n minus 1 times x times d n minus 1 y over d x n minus 1, plus etc. all the way down to, say, a1 of x dy dx plus a naught of x times y is equal to some function of x. Right, so we see here that there's actually no intermingling. We have a derivative with respect to the n minus first derivative of y here, but we have no other orders of y multiplied by that term. Again, nth derivative of y, nothing else, y all by itself, so all these guys are sort of just hanging out by themselves. And so when you can write an equation like this, this is what we call a linear differential equation. And, by the way, this is actually an ordinary differential equation. So that's important to note. On a higher level, basically the idea is that this the left-hand side actually will split if you write, say, y1 plus, say, c times y2, and then you can actually split the derivative across both this guy, and so forth, and then that's called the linear property. If you ever go into linear algebra, this will make a lot more sense to you later. But okay, so those are the big ideas from section 1.1, and so let's now talk about section 1.2, right? So taking a look at section 1.2, they give us an nth order differential equation with an independent variable x and a dependent variable y. So for instance, we can talk about, say, second order differential equations. Say ODE. So we have a second order ODE, and what is that going to look like? So it's something that basically has, so it's going to have second derivatives of the dependent variable. Okay, so for instance, if I have this, that is a second derivative, and so let's say I'm taking the square root of the second derivative, I'm adding 1 is equal to, say, y. This is a second order differential equation. All right, and so forth. If I change this squaring to a fifth power or something else like that, then that's going to be a fifth order differential equation, etc. There's two different ways that people usually write this, and they try to write everything in terms of the highest order derivative is one standard way to write it. So one standard form that you could see this in is dy dt squared plus 1 is equal to y squared, and that would tell us that we have d squared y dt squared is equal to y squared minus 1. By the way, this says this is the nonlinear differential equation, right? So this would be a standard form where you isolate the highest derivative and you set it equal to the rest of the stuff. And so the book itself gives you a couple of different forms. So they say basically, if you can write this as an equation like this, so you have some function f, we don't know what that f is, so dy dx and say all the way up to dny dxn is equal to 0. So if you can write this as a function that involves up to the nth order derivative, then this is an nth order ODE, right? So in the first case, basically I could take, say we call this star, then if we want to show this, then we'd have, move everything over to one side, we'd have square root of d squared y dt squared plus 1 minus y is equal to 0, and this would have been our big F. And another way that people sometimes write nth order differential equations, like I was saying, is you take the highest order derivative, so dny over dxn is equal to little f, x, y, and derivative of y with respect to x, etc., up to the n minus first derivative, dx n minus 1. So these are two standard ways we can write this. Again, you're never really going to have to bother with this or this, but we're just trying to be precise exactly what this means. So these are two ways of characterizing nth order derivatives. Okay. Now, what we want to do is we want to talk about solution concepts. And so we're going to talk about definition. We're going to talk about explicit solutions. Okay. So a function, say phi of x, that when substituted for y, or say for the dependent variable in a differential equation, satisfies the equation for all x in an interval I, then we say that phi of x is a solution to the differential equation, I'll say ODE, over I. Okay? So these are kind of tedious definitions. This is sort of what you would guess if I told you that this is what a solution is. But we need to make sure that we're precise on what we mean. So, so here's an example. Suppose that we want to show that x squared minus x to the negative 1 is an explicit solution to the linear equation where we have d squared y. So second derivative of y with respect to x, not t, minus 2 over x squared times y is equal to 0. All right. So show that this, what we're going to call this phi of x, is an explicit solution to this differential equation, but psi of x equal x cubed is not a solution. Okay, cool. Let's take a look. Okay, so what we're going to do is basically we're going to try to plug things in. So we have this guy, so we have d squared y over dx squared minus 2 over x squared y is equal to 0. We want to go ahead and plug in, say, phi double prime into here. We want to plug in phi into here. So that means we need to find phi double prime. So phi prime, well, let's go ahead and just write phi of x is equal to x squared minus 1 over x. That means that phi prime of x is going to be 2x minus 1 over x squared, and then kicking out a minus sign. And finally, phi double prime of x is equal to 2 plus minus 2 over x cubed. And again, this is just using the power rule. That is a 3 in the exponent. Let's see if we can pretend like I moved it up higher. There we go. There we go. That looks kind of like it's an exponent. Let's say it is. Okay, now let's go ahead and throw these two guys into our differential equation. So, so plugging it in, we have, say, we're putting a second derivative, minus 2 over x squared times the original function is equal to 0. And so now I'm going to have 2 minus 2 over x cubed, and now I'm going to have 2x plus 1 over x squared. And so I don't know this is equal to 0 yet, so I'm just going to take that off, and now I'm going to go ahead and try to see that it actually turns into what we want it to. All right, so this first term, I'm just leaving it alone for now, so 2 minus 2 over x cubed. And I'm subtracting whatever I get when I multiply by 2 over x squared. So looks like I'm going to have, oh, sorry, I copied the wrong thing in there, didn't I? This wasn't phi, that was phi prime. This should be x squared minus 1 over x, my mistake. Okay, so now when we multiply this through, we should get something much better. So the first term, x squared cancels with x squared, and so that's going to leave me with just 2. And then I'm going to have minus 1 over x, and then that's going to be multiplied by 2 over x squared, so that's going to be minus 2 over x cubed. All right, well, this term and this term are the same, and we're subtracting them, so guess what? This is 0. Boom, that is the solution. So we say phi satisfies the ODE and is thus an explicit solution. Okay, good. All right, now let's try the other one. So they told us to show that psi is equal to x cubed is not a solution. So again, we need to find this first and second derivatives of x cubed. So it's going to be psi prime is going to be 3x squared, and psi double prime is going to be 6x. Now, if I go ahead and plug those in, I see that I'm going to have second derivative of y minus 2 over x squared times y itself is equal to something. So putting in the second derivative, I get 6x. Putting the original function, I get x cubed. And now let's see what these add to. I have 6x minus 2 times x is equal to 4x. But this is not the 0 function. So, psi is not a solution to the ODE. Done. Okay, so that was that example, and so that's an example using of an explicit solution to a differential equation. Let's find another one. We want to show that. Let's see. So we have example 2. Show that phi of x is equal to, say, c1 e to the minus x plus c2 e to the 2x is a solution to y double prime minus y prime minus 2y is equal to 0 for all choices of c1 and c2. Okay, well, you are going to become very familiar with these after we get through chapter 4, and by the time we finish chapter 7, you'll have about a dozen ways of solving this particular equation. Okay, so what we have now is we have a something we think should be an explicit solution, and we have to plug it in here. Now we see that we have a second derivative, a first derivative, and the original function itself, so we're going to need all three of those. So let's go ahead and compute phi prime of x. Phi prime of x is equal to minus c1 e to the minus x, and then plus 2c2 e to the 2x. And phi double prime of x is equal to c1 e to the minus x plus 4 c2 e to the 2x. Putting all these together, so I'm now going to put second derivative minus the first derivative minus twice the original function, and we want to see what that is equal to. So let's see, putting in the second derivative, I get c1 e to the minus x plus 4 c2 e to the 2x, and I put in the first derivative, so c1 e to the minus x plus 2c2 e to the 2x. And then I'm subtracting the original function, which is going to be c1 e to the minus x plus c2 e to the 2x. All right, now we want to show that all of these add up to 0, ultimately. All right, so let's go ahead and work out what this is. So collecting all the terms that involve e to the minus x. So I have e to the minus x. The first term that's going to give me a c1. Here I have a minus times a minus c1. So I'm going to have plus c1 here. And then I'm going to have minus 2c1 here. Right? And then everything connected to e to the 2x. I have a 4c2. I have a minus 2c2 from the next term. Then I have another minus 2c2 the next term. Okay, well, this is 0, and this is 0, so this is equal to 0, check. And so phi is an explicit solution to the ODE. And just make sure when you work out your answers, you give me a nice solid conclusion here to all your work. If I just see these equations and you don't tell me what it means, then yeah, that just makes life harder on me. Okay, so there we go. That is example 2. All right, now the next one is previewing an implicit solution, and they hadn't even defined it yet. So let's talk about implicit solutions. Okay, so what is an implicit solution here? Let's see. So here we have, as an example, before we actually define it, just following the book, I'm going to show that the relation y squared minus x cubed plus 8 is equal to 0 implicitly defines a solution to the differential equation and this is going to be dy dx is equal to 3x squared over 2y. And by the way, this is a nonlinear differential equation. You're not allowed to have 1 over y's. Okay, so let's go ahead and do this. So that was a minus sign here, and there was a y squared up here. Well, let me just clean that up. Squared minus. Okay, so how do we do this? The language of implicit solutions sort of hints at what we need to do. We need to take implicit derivatives. So if I want to take an implicit derivative, basically I'm going to be running with the chain rule, and I'll send you guys an extra video talking about that later. But yeah, let's go ahead and do it. So the implicit derivative of this guy, so basically we're taking d by dx of y squared minus x cubed plus 8 is equal to 0. So taking derivative of both sides. So we're treating y as a function of x. So that means we're going to be using a chain rule. So this is going to give me 2y times dy dx. Now x is naturally a function of x, so we're just going to not have a chain rule popping out. So it's going to be 3x squared here out of this term. Plus the derivative with respect to x of a constant, which is 0. So plus 0 is equal to 0. Clean that up a little bit. Put a square there. Okay, now what we're going to do is we're going to solve for the differential equation. And we see that what we're left with is we have 2y dy dx is equal to 3x squared, and then we divide by 2y. So that's going to give me dy by dx is equal to 3x squared divided by 2y, right? And that is the differential equation that I am in fact looking for. So yes, this relation implicitly defines a solution for the ODE. Okay. Good. All right. So let's do another one. All right. So here we go. Example 4. We want to show that we have x plus y plus e to the xy is equal to 0 is an implicit solution to the differential equation, the ODE. This is 1 plus x e to the xy times dy by dx plus 1 plus y e to the xy is equal to 0. Okay, so I'm going to just do the same routine, and then I'll actually give you a definition for the implicit derivative. All right, so let's go ahead and do it. So solution. All right, so I implicitly differentiate both sides. I'm taking d by dx of x plus y plus e to the xy is equal to 0. So I'm going to have just 1 plus dy dx plus, now we're taking the derivative of this, but remember we're treating y as a function of x. So this is going to be e to the xy times the derivative of x times y. So x times y of x, right? And so we're going to basically use the product rule. So that's what's going on here. So that's going to give me y of x plus x times y prime of x. And this is equal to 0. Okay? Now, instead of y prime, maybe I should have written dy by dx. And we're just, instead of y of x, I'm just writing y. Okay, well, there we go. All right, now we solve for dy dx. And so I'm going to have dy dx minus x, or plus x e to the xy on the left-hand side. So I'm just going to say that. I'm just basically distributing this guy over and I'm pulling it out. And on the other side, I have minus 1, and then minus y e to the xy. Right, and now if I divide both sides, oh wait, this is probably more than I need to do. Yeah, this is more than I need to do. Just looking at the equation here, if I just keep everything on this side, I'm basically done. So basically I had, after distributing this through and factoring out dy by dx, and that's what I got here, I'm left over with this and this term here, and that matches exactly what we were looking for. So, yes, this relation implicitly defines a solution to the ODE. I swear my handwriting is usually better. I just have sweaty fingers today. You do not need to know that. Okay, so let's take a look. So what is an implicit solution? Okay, so a relation, say g of xy is equal to 0, is said to be an implicit solution to a differential equation on the interval I if it defines one or more explicit solutions over I. Okay, and so basically the whole idea is that we're using what's called the implicit function theorem. When you have a relation like this, then you are making an assumption, and then when that is satisfied, if you choose this guy to be your independent variable, it implicitly defines a function on y. So for instance, I could have x squared plus y squared is equal to, say, 1. And this, we know if we wanted to, we can actually solve this. This would be y squared is equal to 1 minus x squared. And then that gives me two different continuous solutions. One where we take the positive part, one take the negative square root of y. So this would give me two different equations, and this would actually be a solution to a differential equation if we take a look at what happens when we take and the implicit derivative. So this would give me 2x plus 2y dy dx is equal to 0. And so then this would then tell me that dy by dx is equal to minus x over y. And so this relation gives me two solutions to this differential equation. So I can say that. So the relation x squared plus y squared is equal to 1 gives two explicit solutions to dy over dx is equal to minus x over y for x in the interval -1 to 1. Right? So this is so this is basically an implicit solution to this guy. Okay, cool. All right, so now we have a few ways of talking about solutions of differential equations, and now we're going to get into initial value problems. Okay, so now let's talk about yet another kind of solution that we're going to be concerned with. This is a solution to initial value problems. So what is an initial value problem? Okay. So when we were talking earlier, I was telling you that we were going to have these things called general solutions, where we end up having some constants floating around in the solution to our equations. What this means is that we don't have actually a fixed single solution to a differential equation, but we have a whole family of solutions. And what we'd like to do is find some way to fix what those constants have to be. So, for example, if I try to solve, say, dy dt is equal to, say, just y, then what do I get? I get, say, well, let's just do that whole business with what we call separation of variables. And so this is going to give me a natural log of the absolute value of y is equal to t plus some constant. And so then that tells me that the absolute value of y is equal to e to the t plus c. And we'll just assume, right, for now, that y is positive. So this gives me a whole bunch of constants, and we can write this as e to the c times e to the t, or just say is e to the c tilde e to the t for some other c that has to be positive. Right? Okay. So the idea is that we'd want to know is what is, say, c tilde. And this is really important because, I mean, for a general solution to a differential equation, we do like to know what the family of solutions are. But for any given, say, physical problem, we're going to have some initial conditions that we want to meet. So this sort of problem actually comes up a lot in population dynamics. So for instance, c tilde could represent, say, what your initial population was. And so, and there's that word, initial value from the initial value problem is, well, we need the initial value. So let's say that we have y naught is equal to, say, 100. Well, then what we do is we say, well, I already solved for y, and so I'm going to plug in 0. I'm going to say c tilde e to the 0, and that's just going to give me c tilde. So in this case, it tells me that y of 0, which I said should be equal to 100, is also equal to c tilde. And so there we go, and we fixed a particular solution to this differential equation, and it is this. Y of t is equal to 100 times e to the t. Okay, so now let's talk about what initial value problems are. So an initial value problem, let me grab the book to make sure I'm saying everything just right. So an initial value problem for an nth order differential equation of the form, and we'll put in one of these standard forms that we have: y, x, y, say dy dx up to dy dx to the n is equal to 0. Is a problem where we would like to find a solution to, say, we'll call this guy star, given n initial conditions. All right, so we're going to start with just say y of 0 is equal to something, say y naught, y prime of 0 is equal to, say, y1, and all the way up to y to n minus first derivative at 0 is equal to yn, or minus 1. Now, it doesn't actually have to be starting at 0, for instance. There's plenty of differential equations that we'll want to start at a later point. So what I can do is, instead, I'm going to say our initial point is going to be at x naught. So y is n minus 1 of x naught, right? And so this is going to be the initial value problem for this differential equation, and it involves n initial values, where they start at 0 and they go up to n minus 1. Okay, so we can go ahead and take a look at another example. That was a really straightforward one I gave you earlier. So what we want to do then is we're going to show that phi, which is equal to sine of x minus cosine of x, that we want it to show is that this is, say, we want to show that phi is a solution to the initial value problem, where we have, say, dy dx squared plus y is equal to 0, and we require that y of 0 is equal to -1, and y prime at 0 is equal to 1. All right, so that's what we're looking for. All right, so we just want to show that this works, and so I guess it's the right solution. So what we're going to need to do, well, we need to plug in phi to make sure it even solves this differential equation in the first place. So that means we're going to have to take derivatives of phi. So phi prime is going to give me, say, cosine of x plus sine of x, and phi double prime is going to give me minus sine of x plus cosine of x. And so if I plug that in to my differential equation, I see that phi double prime plus phi is going to give me minus sine of x plus cosine of x plus cosine of x minus, sorry, my mistake. This is what I should be putting in there. Sine of x minus cosine of x, right? And if this is 0, then it solves the differential equation. That's what we're looking for. We're trying to show that this is going to be equal to 0. Well, I say that I have a minus sine of x, and I have a plus sine of x, and I have a cosine of x, and I have a minus cosine of x here. And so, indeed, this gives me 0. So check is a solution to the differential equation. But is it a solution to the initial value problem? So let's check it out. So you see at phi of 0 is sine of 0 minus cosine of 0, so it's equal to -1. And then we see that that matches there. So that's check. And let's see, phi prime at 0. Well, this is phi prime, and so that's going to give me 1 plus 0. So that's equal to 1. And y prime of 0 should have been 1. So that's a check too. Okay, so phi is then a solution to the initial value problem. And that's because it is a solution to the differential equation, and it is also satisfies the initial values. And so since it has those two things, that means that it must be a solution to the initial value problem. And so we're done. All right, now the next example gives us something that we're going to be running into a lot more frequently. We won't usually be given a solution to initial value problem. What we're going to want is we're going to find a solution to the initial value problem. And so we'll have a general solution. So we'll say a general solution to, say, this differential equation, d squared y over d x squared minus dy dx minus 2y is equal to 0. So a general solution to this differential equations is given as, say, phi of x is equal to, now it's going to be in terms of some constant, so e1 times e to the minus x plus c2 times e to the 2x, where c1 and c2 are real constants. So we can choose c1 and c2 however we want, and this will always be a solution to the differential equation. And so what we want to know is find c1 and c2 to determine a solution to the initial value problem with the initial values, say y of 0 is going to be equal to 2, and dy dx is equal to minus 3. And let's say at 0 it's equal to minus 3. Okay, so let's go ahead and do that. All right, so what I'm going to do then is I just take my phi, and I'm going to need phi, which is c1 e to the minus x plus c2 e to the 2x, and I'm also going to need phi prime, so let's go ahead and calculate that. So it's going to be minus c1 e to the minus x plus 2c2 e to the 2x. All right, now let's plug in 0 into phi. So into phi, we put in 0, and we get c1 plus c2, and that's equal to 2. Now in phi prime, if I put in 0, then what do I get? I get minus c1 plus 2c2, and that gives me minus 3. Okay, so now we have a system of equations. And this just goes straight back to regular algebra, if you want. And so we need to find a way of solving this. Well, I say I have a C1 in this equation and a C2 and a C minus C1 in this equation. So if I add them together, that'll just cancel. So then I see by adding equations, then I get, say, 3C2 is equal to -1. And so that tells me that C2 is equal to minus 1/3. And then if I plug that back in, I see that C1 minus 1/3, this is using the first equation, is equal to 2. And so that tells me that C1 then is equal to 2 and 2/3, 2 plus 1/3. And so it's going to be, what, 6, 7/3. Right? And yeah, so then, so the solution to the IVP is given as, we have phi of x is equal to 7/3 times e to the minus x plus, or say, minus 1/3 e to the 2x. And that's the solution to the initial value problem. Okay, cool. So that's not too bad. So this is what you're going to see more typically. You'll have a method that'll give you some sort of solution to a differential equation. This particular problem we'll be able to solve easily after we get past, say, chapter 4. And actually section 4.2, I think, covers this exactly. And then once we get there, it will end up throwing out these C1 and C2s, and we need to find a way to resolve them. And the way you do that is you use the initial values to set up constraints, like we did here. And then after that, it's just algebra. Okay, so not too bad. So then you're left with this last question, is when is there a solution to an initial value problem? So when can an initial value problem And that's a really good question. And so what I'm going to tell you here is it's a specialization of a much more general statement called the Picard theorem, or the Picard-Lindelof theorem, if you want. And so I'm going to call this theorem, we're going to call it the Picard theorem, or Lindelof theorem. I probably got the Lindelof wrong. I think it's supposed to be maybe an umlaut on the O, and there might be another F. I mean, who knows? I apologize to Lindelof, who's been dead for a century. Any case, so we have basically, so we say consider the initial value problem where we're given, say, dy dx is equal to f of xy, where we have, say, y of x naught is equal to y naught. And basically, if f and dy dx are continuous in some rectangle containing, say, x naught, y naught. So, wherever this is in space, say this is x naught, y naught. As long as it's continuous in this rectangle, wherever that is, or it could be a little tiny circle or whatever you want. We generally just say in a neighborhood. Then there exists a delta. Let me just write an actual delta. I say a delta greater than 0, so that this problem has a unique solution over, say, x naught minus delta to x naught plus delta. So we can go a little bit backwards in time, and we can go a little bit forwards in time, and that's all we know. And so basically, it tells us that if we start here, we can go for some small segment, and that's all we know, and then we'd have to reevaluate when we get over here. There's a couple of examples that we can go over about this that are interesting. So for instance, if I go ahead and, well, let's see what their examples are. We'll just do one example from there. So let's talk about one example from the book, and I'll add on a couple others. So for the initial value problem, where we have, say, 3 dy dx is equal to x squared minus xy squared, and we have, say, y of 1 is equal to 6. Show that there exists a unique solution to this IVP. Okay, so what do we want to do? Okay, well, actually, I kind of gave it away. The theorem says, does theorem 1 imply the existence of a unique solution? And the answer is yes. And the reason why is that if you take a look at, say, dy dx is equal to x squared minus xy squared over 3, well, guess what? It's a polynomial. So it is continuous, and its derivative is continuous with respect to y. Did I say y back here? I think I did. Oh, no. I made a mistake. Oh my goodness. That should have been df dy. I don't know why I wrote the other one. And that should be a partial derivative. All right, let me correct that. df by dy. I am sorry for that mistake. But yeah, okay. So if f and the partial derivative of f with respect to y are continuous, then you win. That's what I should have written. Okay. So now I see that, basically this is going to be my f of xy, and so it is indeed continuous with respect to x, and the derivative is indeed continuous with respect to both variables. Okay, so we're good. It's a polynomial. It's easy. It works, right? It doesn't matter what neighborhood we look at. We were looking at, say, 1, 6, but it would actually work for any other point. So good. So yeah. So now let's talk about some where we have some problems. So that was a positive example, and so let's talk about this example here, where we have that last one was a positive example. Let's give a negative example. So let's take a look at dy dx is equal to square root of y. And in this case, what we're going to be looking at is we're going to be looking for a solution to initial value problem of y of 0 is equal to 0. Now, if I take a look at this here, this is my f of xy. Indeed, for x, it seems to be continuous, but for y, in a neighborhood of 0, it's undefined for y negative. And indeed, if I take a look at, say, df by dy, we end up getting, say, 1/2 of 1 over square root of y, and this has a vertical asymptote at 0. Now, it actually does have a solution. It actually has multiple solutions, and so there is a solution to this, but it is not unique, and that's why Theorem 1 does not guarantee a unique solution. And we can show this pretty quick. I mean, first of all, note that y of x being always 0 works. Because that means that y prime of x is equal to 0, and then that means that, say, dy by dx is equal to 0, but that is the square root of 0, but y is always 0, so it's squared y, right? So that would work. Now let me show you another solution, though. So what we can do is we can use this whole separation of variables I've been showing you before. So we have dy over square root of y is equal to, say, dx, and that tells me then that I get this solution where I have, say, 2 square root of y when I integrate the left-hand side is equal to x plus c when I integrate the right. And so then that tells me that y can be written, a general solution to this is going to be y is x plus c over 2. Now I need to figure out what c is, but if for my initial value problem, I have y of 0 should be equal to 0, and so that tells me that then 0 plus c over 2 should be equal to 0, and so that tells me then that c must be equal to 0, because the square root of c over 2 is 0. Okay, so then that tells me that y is equal to the square root of x over 2, and that's another solution. To the IVP. Right, so this is sort of a cautious tale, saying that sometimes if you're not careful looking at your differential equation, you can actually have multiple solutions pop out. Now let me tell you one last thing. So notice that we were in the proof, in the conclusion here, we were told that we have some delta where over some small interval we're guaranteed a solution. So I said up here, if we started at where that dot is here, then we can guarantee that we can move forward by some segment from, say, x of naught to x naught plus delta, but we can't guarantee beyond that. And one example is this one. This is one I really like using in academic papers because people often ignore it. So this is an example. It is going to be, so theorem 1, so let's say that we want y of 0 is equal to, say, 0, right? I know I keep using that, but it'll make things easier here. So this is actually a initial value problem that only exists for a certain time, length, and afterwards it actually has what we call a finite escape time in engineering and systems theory. And in fact, it is this sort of thing that keeps coming up in a lot of engineering papers. I find that people are sort of assuming too much of their systems, and they forget that these sort of things can happen. So I've criticized a good number of papers and even rejected 1 or 2 based on what I'm going to describe to you here. So essentially, what we have is we have this differential equation and we have an initial value problem. So theorem 1 says there exists a unique solution to this differential equation because f of xy being given by y squared plus 1 is continuous in a rectangle around 0. It's a polynomial, so it always is. And df by dy of xy is equal to 2y. Is also continuous in a rectangle around 0, right? So we're starting at this initial value, and we're saying basically for any rectangle, it's going to be continuous because it's just a polynomial. Okay, so there's a unique solution, but over a small increment. That's what it always tells us. And so let's look at what the solution to this differential equation is. It's actually not too hard to figure out. If we use, again, separation of variables, what we get is we see that we have dy over y squared plus 1 is equal to dx. And so then integrating both sides, I get arctan of y on the left is equal to x plus c, and then I see then that y is equal to tangent of x plus c. And we know that y of 0 is equal to 0, and that means that tangent of 0 plus c is equal to 0. So that means that tangent of c is equal to 0, and so that tells us that c must be 0. That means then that y is equal to just tangent of x. There's a bunch of ways you could have seen that, but there you go. So what's the problem? Well, if I take a look at a graph, we know, all right, so tangent looks something like that, but by the time we get up to pi over 2, we have a vertical asymptote. And so, and at minus pi over 2 as well. So we see that we aren't guaranteed that there will always be a solution for arbitrary time in the future, but we can guarantee just sort of a small segment there'll be another step forward. So I think that's interesting. Okay, so there you go. That is basically your intro to differential equations. So in this lecture, we have introduced what a differential equation is, and we talked about linear differential equations and PDEs and a little bit of that, just quick definitions, nothing too involved. But then 1.2 basically tells you what we're going to be doing in this class. 1.2 is all about solutions to differential equations. And so we have implicit solutions, we have explicit solutions, and initial value problems. And so most of chapters 2, 3, 4, and what we'll also cover in 7 are all going to be very much concerned with each of these kinds of solutions. In any case, welcome to the class, and yeah, I hope this video isn't too long. If it does end up being too long, this will just really count for 2 lectures. I think I might put in a little bit extra information just about the Picard theorem, just for fun, and then we can jump into section 1.3 next, which talks about direction fields, and in direction fields we end up having sort of a qualitative way of resolving differential equations, or at least getting an idea of what they do. All right, well, it's been a pleasure, and we'll return to my office.
Okay, so hopefully you have some idea of what we're going to be doing now. One nice thing about these sort of videos is going to give me a lot more access to my computer during the lecture. So I can include things like graphs and other things to help you get a better idea of what's going on. In any case, if you're my student, one thing I would like to emphasize is don't comment on the video on YouTube, comment back in Canvas. I'll leave all the announcements to be able to have a discussion underneath them so we can keep everything in one place for each lecture. And but I would like to protect your privacy, and so please only comment on Canvas. All right, well, that's it for lecture 1, and yeah, I'll see you next time.